In this video, we'll do another definition of the derivative example. So first I want to talk about some notations that we have for the derivative. The first we've already seen. If my function is y equals f of x, I could write the derivative as f prime of x. If we call our function y, we could also just write y prime. We've also seen the notation that looks like a fraction, although it's not technically a fraction, so I don't say df over dx. The way I say this in words is I say df dx. All right, and there's a similar notation if I change the f to a y. If I'm calling my function y, I could write it as dy dx. So in this notation, when we write something like dy dx, that represents my derivative. And a derivative is an instantaneous rate of change, or IROC for short. But notice that this is like delta y over delta x, just in terms of how it's written. And delta y over delta x, that is an average rate of change. So this df dx, or this dy dx notation, is supposed to be similar in structure to what an average rate of change looks like. And it just helps us remember, oh yeah, derivative it's a rate of change. Okay, so let's do an example where we find a derivative using the definition. So let's let y be 1 over the square root of x, and part A asks us to compute dy dx using the definition of the derivative. So dy dx is going to be equal to the limit as h approaches 0, okay, of my function at x plus h, in this case it's y evaluated at x plus h, minus y of x all over h. So at this point, we just know one form for the definition of the derivative. It's this limit as h approaches 0. In the next video, we'll learn a new form for the definition of the derivative involving x, and as x approaches some number, but let's not worry about that for right now. All right, so let's start to evaluate this. We have the limit as h approaches 0. So if I plug x plus h into my function, we get 1 over root x plus h. And then minus, if I just write y of x is 1 over square root of x. I'm leaving myself some room here deliberately. And then this all over h. Because on the top, I notice I have a fraction minus a fraction with different denominators. So to combine them, I'm going to need to get a common denominator. The first fraction I can multiply by on the top and the bottom by root x. And the next fraction I would multiply by on the top and the bottom by root x plus h. So root x plus h over root x plus h. So if we simplify now, we get the limit as h goes to 0. The first fraction becomes, I get this root x on the top, and my denominator is going to be root x plus h times root x. In fact, if I just combine both of the fractions into one now, I'm going to subtract this other numerator, which is the square root of x plus h. So we have this all over that h on the bottom. So now the numerator has a bunch of square roots, but on the top of the whole fractional numerator, I have a square root of something minus square root of something. And that makes me think of the conjugate. So for this fraction on the top of this big fraction, I'm going to use the conjugate. I'll multiply by root x plus h. And then same thing on the bottom, root x plus h. So notice I'm just working with this fraction that I have on the numerator. So this will give us the limit as h approaches 0. And now on the top of this, when I multiply out, I'll get x. That's root x squared. And then I'll get minus the second term squared. That'll get rid of this other root. I have to make sure I put a parentheses, x plus h, so I don't forget to distribute this negative sign to the stuff that comes after. All right, so this all over, let's see, we have root x plus h times root x. That's getting multiplied by that root x plus h. So we have all of this, whoops, over all of this, over that h on the denominator. And now I'm going to write that as a fraction, as h over 1. Because when I divide by a fraction, that's going to be the same thing as multiplying by the reciprocal. And that'll be one of the things I do next. So we get the limit as h approaches 0. So after I distribute this negative x, the x's will cancel, and I'll be left with a negative h over root x plus h times root x, parentheses, root x plus h. And now I'll multiply by the reciprocal of h over 1, which is 1 over h. And now we see something nice happening. The h's are going to cancel. H's will cancel. And once they've canceled, now I'm going to be good to plug in 0 for the h. So I'll be left with a negative 1 on the top. On the bottom, I'm plugging in 0 for the h. So I'll get square root of x times the square root of x, parentheses, square root of x, plus square root of x, a lot of square root of x's. So we get negative 1 over root x times itself is just x. And then root x plus root x is 2 root x. All right, so we have negative 1 over 2. And then x root x, that's x times x to the 1/2. The x I can think of as x to the 1. Because when I multiply these, I have to add the exponents. And that gives me x to the 3/2. So I'll get 2x to the 3/2. And that is it. I have evaluated this limit. So that is my derivative. That is the derivative of 1 over square root of x. All right, let's do part B of this example, which asks me to find the instantaneous rate of change of y at x equals 4. So remember, instantaneous rate of change is a derivative. I need to find the derivative dy dx at x equals 4. So I have a notation for taking a derivative and then plugging a number into it. When I use this dy dx notation, I write this vertical line, and then as a subscript, I write x equals and what I want to plug in. In this case, it's 4. So this notation just means, this is notation for plug in x equals 4. Oops, x equals 4. So if we do that, we get negative 1 over 2 times 4 to the 3/2, which equals negative 1 over 2. And now I've got to figure out what 4 to the 3/2 is. So let's do a little review of fractional exponents. 4 to the 3/2. Well, having that 2 on the bottom means I take a square root. And then the 3 on the top means I cube that. So square root of 4 is 2. And then I'm going to cube 2 to get 8. So that is what 4 to the 3/2 is. It's just 8. So this gives us negative 1 over 16. And that's our answer. So we have finished learning about the first form for the definition of the derivative. In the next video, we'll talk about this other form that involves a limit as x approaches a.